nice to see you guys. Let's see here. In terms of procedural stuff, before we get started, just out of curiosity, how many of you guys ended up turning in homework 0? Good, most of you, that's great. If you didn't, I still strongly urge you to just give it a try on the Athena machines, make sure that you get it up and running like ASAP, so you make sure that all of our systems are a go for future assignments, okay? So now that that one's done, your first real homework is out, right? That's homework 1. I believe it's already posted. Yeah, so it's already on the Stellar page for this site, which means that it is due 2 weeks from yesterday. And essentially by the end of 1 week. On the 19th. Just kidding, it's due on the 19th. Sorry, got it wrong. Due in 2 weeks from last Wednesday. How about that? I know. Yeah, so it's whatever's on the course calendar goes in this class. I don't trust anything I say here. For instance, in our last class, I spent the whole class thinking it was Thursday. Right, so yeah, so that'll be your first homework. That one is for credit. Let's see, you know the late day policy is subtractive. You lose 25% per day after the allotted number of days, which I honestly forget how many I gave you, and after that is a 0, okay? So if you have a problem, there's some issue, get in contact with me earlier rather than later, and if it's an issue that requires additional late days, I'm going to ask that you reach out to S Cube before I'm allowed to approve it, okay? So that's our basic setup here. Is there any question about procedural stuff before we get started for the day? Excellent. Okay. The other warning is this coming Tuesday is your first nano quiz for 837. The deal with these nano quizzes is that they start at 2:35, and then they go for what? It's like 3 minutes, I think. Yeah, they're pretty short. You'll have 2 options for how to take your nano quiz. You can either do it on your phone or your laptop. We'll give you a URL. That reminds me, Larry and hi Dina, our TAs and I are going to work out the best way to do that. We've had a couple different options in the past. Or you can do it on paper, and we'll bring some scrap paper for you guys. What that means is if you're late to class on Tuesday and you come here after the end of your nano quiz, you will not receive credit for that nano quiz. Okay? And so that's the basic setup. We know that a lot of you guys managed to sleep in past 2:30 on occasion, and so there are 2 free quizzes that get dropped at the end of the semester. Okay? So these quizzes are designed to be easy, and mostly to just hold you accountable for the basic content of the lecture material. Is there any question about that? Yes?
I'm walking all the way here from the cognitive science lab. I don't know, I'm not sure that I'll be able to guarantee that I'll be there at 2:30.
Right, so you can come talk to me after class. You know, the official MIT policy is that your responsibility is to be here for lecture. And unfortunately, the way that we run this, it's hard logistically. We have to coordinate something else. But if there's like an extenuating circumstance or you know, there's some emergency that comes up, of course, we'll find a way to do so. Any other questions about the quiz or your assignment? Okay, so let's get started. So we're going to continue today in talking about geometry problems, which is my favorite part of 837 because I'm a geometry professor, and also a fundamental piece of the computer graphics pipeline. So if you recall from our last lecture, we spent basically an hour and a half developing this diagram here, right, which is the world's most complicated way to draw a cubic curve, or just like a simple arc that connects 2 points and has prescribed tangents. Yeah, so as a quick review, does everybody have like maybe a piece of scrap paper around, or they can look over their neighbor? So what we're going to do is spend like 2 minutes. I want you guys to draw some version of this control polygon. Notice how it's sneaky, it intersects itself. Yeah? And assuming that these 4 guys have the labels that I've given you on the screen, my question is, can you find f of 1/4? Right? If this is a cubic curve. This isn't for credit, this is just for fun to draw a picture. Okay? So I'm going to look at my clock, it's 37, so at 39 we'll do it together. But give it a shot, see if you can draw the cubic arc that has these 4 control points. Alright? Why? Because I asked you to, that's fine. meantime, while you're doing that, try what is the name of the algorithm that you guys are doing on paper right now? What's that? It's a mouthful.
Bezier Curves.
So it's a Bezier curve, and the name of the algorithm is mostly a trivia fact. This isn't the kind of thing I put on an exam. Exactly, to Castle Show, or probably it sounds like you can say it better than I do. Okay. I'll give you a hint. What do you think is your midterm is going to have? That's like the very first problem. So that's 2 minutes on my watch. Does anybody need an extra second, or can I go ahead and show you how we can balance on the board? Okay. So in general, if we want to find f of 1/4, remember what the de Castle-Joe algorithm does is we take every line segment and we kind of move that fraction of the way along the line segment, subdivide and recurse. Right? So here, 1/4 along this line is roughly there. We're not going to be very scientific about this. 1/4 along this line segment is here. And similarly here, right? So now we connect these guys with line segments. Go 1/4 along those, connect those line segment, and go 1/4 along him. So this is the plan. In case this diagram is kind of hard to see, remember our algorithm with control points that don't self-intersect is probably easier to look at, right? So what we did is we took the first, second, and third line segments, divided them into quarters, connected those guys together, divide this guy into quarters, connect them together, and take the point 1/4 of the way there. Okay? So it's the same thing here, it's just hard to look at because it's self-intersecting. Yes?
Just a question, maybe we went over this last lecture, but in terms of like your point of reference, like where you're starting, like what is, from what point for...
Oh, I'm sorry, I probably should have labeled these. Yeah, so I sort of implicitly was reading it left to right, but you're absolutely right, I should have labeled these with numbers. Hopefully that was what you were asking.
Yeah.
Yeah, I'm sorry, that was my
So
mistake.
is it like...
So in general, you'll always assume there's zeros and ones here. And in fact, even if they're not, it doesn't really affect this algorithm that much. And I'll be more responsible for this. Sorry about that. Okay, so what does this curve look like? Remember that it has a tangent that aligns with the first segment and a tangent that aligns with the second. So it kind of makes this loop shape like that. Yes?
Does it matter which way you go on the lines to break it up?
No. Oh, I'm sorry. Yes, absolutely. You're saying, did I, if I went 1/4 from this end? Yeah, that would be f of 3/4. Yeah, thank you. So remember, we talked about the affine property last time. This is 0, 0, 0, and 0, 0, 1. Right, so the 1/4 would be the one that's closer to 0. Yeah. Yes?
How to determine the like 1/4 mark between like the labeled points, but how do you determine 1/4 on the like new lines?
The new guys. Oh, that's a great question. Okay, so I'm going to redraw this because it got a little messy. All right, so the question was, how do we do the second step of this algorithm, right? So again, our control polygon. By the way, if there's ever something you guys can't read, I know we're just getting started with the content of this class, feel free to stop me and I'll try to clarify. Last semester I got feedback that said I had serial killer handwriting. I'm not sure what that means, but I, of course, am willing to improve. Right, so the label of this guy is 0, 0, 0, 0, 0, 1. So if I go 1/4 of the way along this curve, What's the label of this point? 0, 0, 1, 4. Notice I'm skipping all the commas and the F's here just for simplicity. And similarly here, right, remember this is 0, 1, 1. Yeah? So two of the indices are the same. There's a 0 and a 1. And one of them's different. So this is 0, 1, 4, 1. Yeah? And now the question was, what is the label of the next guy? Right? So I connect these with the line. And notice that they have two numbers in common, 0 and a 1/4. Yeah? So if I slide between them, the third one slides from 0 to 1. Remember the ordering doesn't matter, these three guys, that was the symmetry property we talked about. So if I go 1/4 of the way along this line, I get the, what do I get? 0, 1/4, 1/4. That would be the label. Yeah, these are all great questions. Okay, so if you're still a little shaky on this trick of how to subdivide a control structure, I'd encourage you guys just like all throughout the day, once on the hour, to pull out a piece of scrap paper, draw yourself 4 points, and subdivide, and pretty soon you'll be experts in doing it. Yes?
Can you draw the curve one more time?
Absolutely. Yeah, so unfortunately I'm a terrible artist. Roughly, I mean, it has to go through this point, right? So I think it'll look kind of like that. Qualitatively, what do we know? We know that it has to stay in the convex hull of these 4 points. So it can't go outside of this shape. And we know it has to go through this point, or not this point. Oh my gosh. This is 1/4, 1/4. Right? The point that we constructed before. Yeah, that's, this is what happens when I do this live. Yeah, so it doesn't necessarily go through this point here, but this is true, and it loops on itself. So remember last time we showed that the initial tangent is aligned with the first segment, and the final tangent is aligned with the second one, and it turns out if it self-intersects, it loops on itself. That property is a little less, yeah. Okay, well, have I managed to totally screw this up yet, or what? Yes, one
So
more.
what is that point with respect to the curve that we just came up with, though, 0, 1/4, 1/4? Like, what is that point?
That point is nothing. So remember what we'd have to do is one more step of subdivision to get 1/4, 1/4, 1/4, and that's the one that we've got.
So does that become like a quarter of the way through the line, or half?
Exactly, a quarter of the way through. Yeah. So that's what we drew before, but I erased it and forgot. Yes.
So we review the symmetric affine and diagonal.
Absolutely.
That's what they mean
Yeah.
visually.
Sure. Right. So our function, it takes 3 numbers. Let's say f of a, b, and c, like that. Right? And essentially, the symmetric property says that this is equal to f of a, c, c is equal to f of b, a, c. And then I can flip the inputs any way that I want. It's the same point. Right? So this is the symmetric property. We've got the affine property, which says that f of, let's see, how do I want to go? T times a1, 1 minus t, a2, like that. So in other words, I'm kind of drawing a line between a1 and a2. Does that make sense? That's what this t value is. Like if t is 0, yeah, then I have a2. If t is 1, I have a1 because of the coefficients of these things. So it's like drawing a line.
So is this equal to your
Yeah, I haven't given you the right-hand side yet. I'm just asking, do you understand what this expression is? Right? This is interpolating between a1 and a2, right? With a slider that's t. And essentially what this says, this is equal to t f of a1, b, c. And that's the property that we're using to like draw along the line and choose a point, like that 1/4 point. Okay? And then what is the third property? I actually forgot. There's symmetric, there's affine. Diagonal. Yeah, sure. And that's the f of a. Remember that this is the blossom and this is the cubic curve that we're really trying to draw. Right, so at the end of the game, at the end of the day, the name of the game here is that we have this function big F, right, and we have these 4 sample points from it. And when we keep interpolating along it, eventually we manage to get like 1/2, 1/2, 1/2. And we know that's the point on the curve. Okay? this is all the construction from the last lecture, so I'm going to encourage you guys to give it another shot on your paper, and at the end of the lecture, if you're still stuck, come chat with me and we'll figure it out. Does that sound good? Excellent. So as a little bit more review, so essentially the idea here is that this cubic arc is defined by 4 points, and actually we can just give an explicit formula for all of the points along the arc. So if you don't like Ducastle-Jones algorithm, you can also just plug into this thing that I have down here. Right? So the coefficients as a function of t are called the Bezier polynomials. Right? And essentially you can think of it as you have a weighted combination of these 4 points, which is tracing out this green curve here, and at different t values give different points along the curve. Right? Okay. Right, so today, if you recall, last time I set you out with a question to think about, which was, okay, these arcs are interesting and they're smooth and they connect 2 points, but that's all they do, right? I can't capture really crazy things that contain more than 4 points, right? And that's our job for today. So in particular, what we found is if we have, for instance, 1, 2, 3, 4, 5 points we want to interpolate with the polynomial, some really crazy phenomena can happen. So for instance, if I interpolate these 5 red points here, probably what I would expect is just like kind of a nice increasing thing. But if I kind of follow the polynomial thing that we laid out in our last lecture, you end up with this weird feature up here, which is a little bit unexpected. Fun trivia fact, this is called the Runge phenomenon, R-U-N-G-E. I believe it's German, and I'm sure I'm saying his name improperly. And this is this idea that the higher your degree polynomial, the more unstable the interpolant is. Right? And so rather than interpolating with one really crazy polynomial, here's my favorite diagram in like any math book, right? We saw this last time. Probably what we want to do is squash together a bunch of polynomials to draw this curve with some nice conditions on how they glue together at their endpoints. Okay? And the name for this construction is the spline. So here we think of a spline as a piecewise polynomial with a high degree of smoothness where the different pieces meet. Are you guys familiar with the term piecewise polynomial, what that means? You can probably kind of guess, right? This is a function where like between 0 and t, it's one polynomial, and then from t to some other t, it's another polynomial, and so on, right? So like, if we were to plot our function, it would look, you know, like a nice smooth function, you know, that maybe is a parabola like this, and then we draw a little cut, and then another parabola like this, another cut, and so on. Okay? So that's this idea that it's piecewise, meaning that between 0 and t naught, maybe I have one formula, between t naught and t1, I have another, and so on. Yeah?
Does the high degree of smoothness mean that it's differentiable?
Right, so that's exactly a great question. So for instance, let's say that I had 2 parabolas meet and it looks like that, like a bird. That wouldn't be a particularly good meetup point if my goal is to draw a smooth curve, right? And we're going to formalize that in just a minute. Okay. Right, by the way, I managed to find a photograph of what this looks like. So here's an actual spline. You know, this term comes from shipbuilding. By the way, I will gladly offer like a useless amount of extra credit to anybody that manages to do this at home. But a spline really does come from like people building boats. And so what they would do is they take this piece of wood here and they heat it up with in kind of a humid environment so that it was bendable. And then, you know, when you design the bottom of your ship, you kind of pin the wood at different points, and then the shape the wood takes everywhere else is called a spline. If you take my graduate course next semester, you will actually prove, I think, on one of the homeworks that the thing that you get really is piecewise polynomial if you do this physical system. So it's kind of cool. This actually works out. Okay. So our plan for today is to actually, the first thing we'll do is answer the question we just got, which is how do we define things like continuity and smoothness? And then we'll talk about one more basis for curves called B-Splines. And then finally we'll be done with curves and start talking about surfaces. If I recall from the last year or two while I've been teaching this class, this one tends to go long. So what I might do is just kind of get to where I get and then stop and continue next time. So that's, if we kind of stop in the middle of this story, that's going to be the reason why. Okay? And intuitively, our goal for today is pretty simple. Right? We have 2 short, you know, curves in whatever your favorite cubic basis is from last time. And our goal now is to have machinery that glues them together so that, you know, if I'm an artist and I'm using these curves to draw a shape, I don't notice the fact that they're actually 2 things, right? That they're glued together in a nice way. So, of course, I've been using the word smooth really informally. And those of you who've taken enough calculus classes know there's a lot of different definitions that make sense here, right? There's continuous, differentiable, k times differentiable, infinitely differentiable, analytic, whatever. And so we should go through it and see what folks think of as smooth in the geometry world. Yeah? And remember from last lecture, this is a little bit of a difficult thing to capture correctly. Like we had this example where you have two different curves that are both functions of t. And as functions of t, they're different curves, but as shapes on the plane, they're the same. And that's where smoothness gets a little tricky. Right? And so that's what we'll formalize in. So in order to do that, we're going to need just the tiniest bit of differential geometry, which is an area of math very close to my heart here. And so the basic motivation here is that we want to join together cubic curves. And then eventually, we're also going to use the same machinery to compute surface normals, which are vectors that are perpendicular to a 3D surface, which we need for lighting and shading and rendering and all that cool stuff. Okay. So let's do a quick warm-up. So how would we go about computing the velocity of a Bezier curve? Remember that our Bezier curve is a function of t. We really can think of t as time. Yeah? And so this function p of t here is kind of like giving me the position of a car driving along my curve. So at time 0, it's on the left point. At time 1, it's on the right point. Yeah. Then what does the velocity look like, and how would I compute it? Any ideas? Yes. Take the derivative. That's going to be the answer to like all the questions in today's lecture. And you're absolutely right. Yeah. And so what does the derivative of this curve look like? Right? So if I have a curve like this, and this is some point, I guess the way it would be here, is p of t. And the derivative of this curve is a vector that's based at p of t, like that, right? And when we talk about taking the derivative of a curve, what we really mean is that we're going to take a derivative of the coefficients with respect to t, right? And what this thing is going to give us is a vector in a plane. Hopefully that satisfies this. Right. So just like we suggested here, we'll take the first derivative with respect to t. And fortunately for us, I think this is something that you guys who took AP Calculus can do upside down while playing the accordion, right? So hopefully it's okay that I'm going to skip this step and just have it on this slide. But let's double check to make sure that, just as a sanity check, we know what we're doing. So for instance, what's the derivative here of 1 minus t cubed? Remember, it's polynomial. You take the 3 down, you get a 2 left. This is 3, 1 minus t squared times d over dt of the inside part. The derivative of 1 minus t is just minus 1. Yeah? So this whole thing is minus 3. And notice that that's the sort of the coefficient of the first term. Yeah? So there's nothing crazy happening in this expression I'm giving you on the board. Notice there are a lot of times in this class when I'm going to do an example of like the first part of a calculation. I encourage you guys to go home and finish the rest, just as a good sanity check to make sure that you see what's going on. It's just I think a lot of this is stuff you've seen before. So it's not to say that if you haven't seen it in a long time, you shouldn't go back and review. Okay. But here's the thing: this velocity, the norm of the vector here, can actually vary as a function of t. Right? There's no reason why this has to be unit norm. And that's actually a little bit of a problem, right? If you think about this analogy of a car driving along our curve, the car is actually kind of speeding up and slowing down as it drives along the curve. But for our purposes in computer graphics, that's a useless signal. Do you see that? Because we don't care how fast the car's driving. We just care about the path of its exhaust pipe, right? Because that's what we're going to draw on the screen. And so when we talk about differential geometry, it's a little bit tricky. We actually don't care about p prime. What we do is we just divide it by its length, and that gives us a unit vector that's parallel to p prime. And this thing is called the unit tangent to our curve, which is totally reasonable. Yeah? And so the idea here is that we're kind of throwing away the information that's irrelevant to doing geometry components. Does that make sense? I think you probably haven't seen this in calculus class. Okay. So, right, so here's our picture here. But the first question I have is what could go wrong with this formula? Anytime, you guys are computer scientists, what happens anytime I have a division? When should I get nervous? 0. Yeah. And there's no reason why p prime can't be 0 here, right? It's kind of like saying my car is driving along the curve, it stops for a second, it changes the steering wheel, and then it drives off in some other direction. Yeah? And oftentimes you'll see curves, for example, with cusps like that. And this might be differentiable as a function of t, but it's not smooth looking as a geometric object. Do you see that? We'll see an example in a minute. And so typically what we do in the theory of differential geometry is we say we define a regular curve to be a curve for which p prime is always non-zero. In other words, this is kind of a cop-out solution to this problem. We just say that we're going to consider curves that have this property. And that's a good thing, because essentially what it does is it avoids curves with cusps. Although when we go back and talk about cubic polynomials, we're going to have to figure out conditions under which that can and can't happen. Right? Okay. So typically, when we talk about the moving tangent along a curve, we also talk about a second vector that moves along the curve perpendicular to it. Anybody happen to know what that thing's called? These are questions I know that you guys know the answer to, but you're not going to answer. This is called the normal vector to the curve. Right? It's perpendicular to the curve. And there are many different ways to get it. One of which is to define that to be the derivative of the unit tangent. And the question is why? Is it clear that if I take the derivative of t with respect to little t here, that I should get something perpendicular to it? This is my favorite two-line proof in math. So let's do it real quick. So what is the one thing that we know about the unit tangent as a function of t? I'll give you a hint. It's called the unit tangent. It has a unit length. Yeah? So let's say 1 equals the length of my unit tangent of t. Yeah? And in fact, for convenience, I'm going to square it. Obviously, 1 squared is still equal to 1. So remember from pre-calculus class that one way to get the length of a vector is to take the dot product of the vector in itself. Right? So this is really equal to t dot product with t. I'm doing this just because it's good to do a little bit of calculus in this class. Eventually, when we talk about rendering, we do physics instead. For now, we can do a little calculus. So what I'm going to do is differentiate both sides with respect to the parameter t here. What is the derivative of 1 with respect to time? This isn't a philosophical question. 0, yeah. And what is the derivative of this dot product? Well, remember the product rule, right? The derivative of something times something else is the derivative of the first guy times the second, plus the derivative of the second times first. In this case, it's the same, so it's really 2 t prime dot product with t. Yeah? And I'm going to add the third thing here. This is saying this is true for all t. What did I just prove? Yes?
Since the dot product is 0, they're perpendicular.
Exactly. Remember that by definition, two vectors are perpendicular when their dot product is 0. And what I just showed you is that for all t, t prime is perpendicular to t. Cool? All right. If you take my class in the spring, essentially all of our proofs are going to boil down to that fact, just over and over and over. So we define a vector called capital K to be t prime, and the one thing that we know about it is that it's perpendicular to t. Cool? Okay, and the picture looks something like what I've drawn you on the screen here, right? Which is the tangent we know is tangent to the curve. And then just because we're in the plane, the only thing that could happen is that K is sort of 90 degrees perpendicular to it. And the length of K is meaningful. So for instance, let's say that my curve were a straight line, right? Then what is t prime? The tangent is constant, right? So t prime is 0. And that sort of suggests the reason that we use K is because K stands for curvature. Don't think about that too hard. But essentially, the idea here is that when K is 0, my curve is a straight line. And as K gets longer and longer and longer, my curve gets more and more kind of curvy. Yeah? One thing that you can prove that we won't prove in this class is that if you take 1 over its norm, this is sort of like the radius of a circle that touches the curve the most closely. And this makes sense. So when K is 0, 1 over 0 is infinity-ish, which makes sense because a line is kind of like a really, really big circle. Yeah, that's kind of what's going on here. Okay. And so if we now take K and divide by his length, then we get something called the normal curve curvature vector, which just points 90 degrees to the curve. So if we take the pair of t and n together, which you guys are going to do on your homework, by the way, this isn't just theoretical, you're going to actually compute these in your next assignment on a curve. You get something called a Frenet frame, which is like this little moving 90-degree frame that moves along the curve and gives kind of a nice basis for stuff nearby. Okay? So if you like this kind of stuff, And then I'll stop talking about my class this spring. You guys should come talk to us, talk to me, and you can come hang out in our graduate class. And for instance, this is used, I've put a pointer here to a research paper that appeared, oh gosh, about a decade ago. Which has to do with simulating shoelaces, which is of course a very important problem in the computer graphics world. I encourage you guys when you're home to pull the shoelaces out of your shoe and do an experiment which they're trying to replicate here, where what they do is they hold on to one end of the shoelace and they start twisting the other end. And what will happen eventually is the shoelace, there's a physical phenomenon where the shoelace will buckle upon itself and make a little loop like this. Does anybody know the name of this loop? I'll be really impressed. It's called a plectoneme. I learned that by working with the people that made this paper. But anyway, essentially by computing moving frames along curves, this is sort of the beginning of a lot of physical simulation for hair and shoelaces and other stuff that shows up in movie effects. Okay, so now that we've developed a little bit of language for how to talk about curves and how bendy they are, we can go back and start thinking about what it means to join two curves together in a nice fashion. Okay, and that's our next task. And sort of what I've already hinted at today is that there's sort of two notions of smoothness of a curve. Right? One is sort of the smoothness that the driver feels while they're driving along the curve in your function f of t. And the other is the smoothness of the curve as a geometric object sitting in the plane. And these are not the same thing. Yeah? And so for instance, here I've given you a gamma of t, where the x component is t squared and the y component is t cubed. These are infinitely differentiable functions, yeah? But if you look at the trace of the curve, it has this cusp here. And essentially what's happened is at t equals 0, the velocity just vanishes for a second. Right? So my car is driving along, it stops, it turns the steering wheel, and then it just heads off in another direction. Right? So from a calculus perspective, this is a smooth object, but from a geometry perspective, it's not. Whereas on the right-hand side, we have a curve with a smooth trace. It's just a parabola. But it's a little bit hard to detect, right? Like, so for instance here, I've made the world's most complicated definition of a parabola. Do you see this? So when t is negative, it's kind of the usual definition, right? X and x squared. When t is positive, I put x squared and x to the fourth, just for fun. Right? So in other words, my car is driving along the parabola, it hits time t equals 0, and suddenly it jams on the accelerator and zips off. But the shape that it makes is still the same, right? So even though the passengers in the car are probably very uncomfortable, as a geometric object, this is okay. Right? And the reason why I'm giving you this corny example is to justify that these are two completely different notions of smoothness, and they don't, it's not like one is a subset of the other. Right? This is not a twice differentiable function, but it's a smooth geometric object. This is an infinitely differentiable function, but it's a pointy geometric object. Okay? Hopefully we've driven that point home. Okay. So in general, if you guys like this kind of stuff, there's an entire area called Computer-Aided Geometric Design, CAGD, which focuses on this kind of work. There's a lot of classes on this topic in our mechanical engineering department. And they're very concerned about it, because for instance, if you're designing your car, you would like to have these nice, sleek surfaces on the side of your car, but you'd also probably like to design them by gluing together a lot of surfaces instead of like constructing one giant function that traces out a whole car. And in fact, a lot of the things that we use in computer graphics to evaluate smoothness actually come from that community, which is kind of cool. So for instance, when I used to work on these sorts of problems, we spent a lot of time essentially simulating. One of the things that people do when they design the side of a car or a piece of sheet metal is they'll take like a t-shirt with a bunch of stripes on it, like that, and they'll hold the metal kind of near it and look at the reflection, which will trace out a bunch of curves on the surface. And if, you know, somehow the way that they deem if the surface is smooth or not is by looking at the shapes of these curves and whether they look like elegant streamlines or not. And it turns out in computer graphics we do precisely the same thing, just virtually. We render these and look at it. And in fact, it's a standard feature that's built into AutoHAS. And what it leads to is a bunch of different notions of smoothness that are all sort of not equivalent to one another, which is a giant headache to keep in your mind. Yeah? And so I've given you the most common ones here. C0 continuity means just two curves meet at a point, and I don't care what happens at that point. In other words, it's continuous. So here's an example of a C0 continuous thing. It can have a kink in it. G1 continuity. So in general, the two letters to be aware of are C and G. Right? C stands for calculus, I guess. G for geometry. right? So C, it says it's continuous, which is a thing we can check with calculus machinery. G1 says that the tangents align with the seam. So if you look really closely at the seam here, by the way, this was a giant headache for me to draw in PowerPoint. What you'll see is that actually if you were a passenger in a car driving along this curve, they turned the steering wheel really, really fast, but they didn't change their velocity in the process. That's what the G1 continuity would be. So the tangent stays smooth. C1 continuity means that the parametric function, this function of time, is differentiable. And C2 is twice differentiable in time. G2 means that the curvature functions match up with the 2 points. Like with the The reason why I haven't put G2 here is that it's actually an area of research to get two surfaces to meet up with G2 continuity. It's an extremely difficult math problem. So the main ones that we'll focus on here are G1 versus C1. And hopefully you can kind of see the difference at this little kink corner. I know that it's a little subtle. Okay, so now let's go back to the machinery that we developed in our last lecture, right? We talked about cubic Bezier curves, which are our favorite things. I think I managed to confuse everybody about them in case you weren't before at the beginning of the lecture today. But remember that they're defined by these 4 control points. And remember that the tangent at that final point is determined by this line segment. Yep. So now that we have a little bit of language here, how can we design control points so that we have C0 continuity when I glue together 2 of these curves? What's my condition? Yes? Exactly. The 4th point of the first curve is the first point of the second. Right? So for instance, if I have 2 sets of control points like this, and then a second one which is like that, then they'll meet up at this point, they share this point, and then they go off. Okay. How can I get... Actually, yeah, let's do G1 continuity. This one's a little trickier. I bet you can get into it. Yeah.
You have to make sure keep your key on.
Exactly. This point, and that point are all on the same line. Does that make sense? Because remember that this determines the tangent at the last step. No? How about C1 continuity? In other words, the car doesn't experience, a crazy hit on the accelerator. In addition to these all being on the same line, what additional condition do I need? Yes?
Does P1 have to be a midpoint?
Exactly. P1 has to sit right in between these other 2 guys. Perfect. And I'm going to let you guys think about C2. That gets a little crazy. Yeah, that's going to involve the 3rd point outline. Okay. Right. And so essentially, you can go through and connect together cubic Bezier curves in this fashion, and guarantee just by checking sort of a finite number of points whether they meet up together in a nice way or not, right? Which is what we were after. So for instance, here you can see that this curve is C0 continuous here. It's G1 continuous here. Notice that the red point is not at the midpoint of the other 2 guys. And then it's C1 continuous here, right? This guy's at the midpoint. Does that make sense to everybody? I should pause and see if there are any questions. Okay. So the good news is we developed something to make curves meet together, right? That was our goal. We had 2 curves, and we now have a way to glue them together in a fashion that we can control the behavior at the point that they're glued together. Yes?
So the curve C1 continuous is also G1 continuous?
Yes. Yeah. Because remember, G1 means they're all collinear, C1 means they're collinear, and they're right at the Great question. You should develop a little Venn diagram at home. It's a good thing to describe. So the good news is we have some condition. The bad news is it's like not a very fun condition, right? In other words, if I mess with the control points of the first curve, I have to modify the control points of the second one to make sure that they continue to meet together. And this is generally something that's not terribly desirable, right? What it means is that you make some local change, and it'll have a global effect on what your object looks like. Yeah. And so another way of putting it is that even just maintaining tangential continuity, you need some constraints that link the control points together. Like the P3 here and P2 there are linked together. They're in time. And so oftentimes, if you're working with an artist, they don't like constraints, right? And when you tell them like, well, if you move this point, that guy's got to go too, the immediate feedback I guarantee that you'll get is Y. Yeah? And so there are a lot of other bases for curves that don't have this property. And of course, we're going to introduce one more basis for cubic curves today. and these are called the cubic B-Splines. And the idea of cubic B-Splines is that they kind of chain together a bunch of control points in a way where they always meet up with tangential continuity. But the drawback is going to be that they don't actually hit the endpoints of the points you prescribe. So they'll always sit inside of them, but they're never going to actually touch them. Yeah? This is actually pretty common, especially for modeling 3D surfaces. I'm not going to dwell on this because this isn't the most popular spline basis ever. It's in the syllabus for this course, so we got to spend 10 minutes on. But the basic idea is that here, P1, P2, P3, and P4 define a segment that kind of sits on the inside, like this red guy. And as I move along, that segment moves along with them. And the way that you do this is that the first guy is defined by the first 4 points, 1, 2, 3, 4. The next segment is defined by 2, 3, 4, 5, and so on. Okay? And the way that you can construct these curves, and I'm going to let you guys do this as a challenge. And by the way, when I throw these things out, what I like is try it on paper, and if you're stuck, post a question on Piazza and work with each other, and I'm also happy to go on there and draw some pictures. Unfortunately, because the way this class is structured, we like do a different topic every day, and that doesn't leave a ton of time to fill in some details. But the way that you can get it from de Castle-Jo's algorithm is to give a slightly different set of labels of points, which is this will be 0, 1, 2, 1, 2, 3, 2, 3, 4, 3, 4, 5, and so on. Right? As opposed to 0, 0, 0, 0, 0, 1, right? Notice, for instance, that these two guys still have 1 and 2 in common. So the affine property still applies, but it just applies in a different, the subdivision rule you'll need for this curve is different. Okay? So I encourage you to try and find, for example, can you find f of? It's actually kind of challenging. it's difficult to get this right. Okay. So for instance, if I took the midpoint here, what would be the label of that?
1, 2, 1 half.
Yeah, it would be 1, 2, right, because those are the two indices we have in common. And then the halfway point between 0 and 3 is 1.5. And similarly here, if I took the midpoint, what would I get? I'd get, well, now I have 2 and 3 in common. What's the midpoint between 1 and 4? 2.5. Yeah. You get 2, 3, 2.5. But then I'm in trouble now. These two guys don't have the same index, right? So you're going to have to think a little bit about how to structure this the way to get what you want. For instance, maybe I go 2/3 of the way along this curve and 1/3 of the way along this curve as a hint. Well, let's try that. Okay. So if you plug in this particular subdivision trick, which takes a little while to get used to, what you get is yet another basis called the B-Spline basis, which interpolates your control points in a different way. Notice that none of these ever get to 1. They sum to 1, but they never reach 1, which effectively implies that your curve never touches the control points that you drew, because that would, the 1 there is saying it's 100% at that control. Okay. Right. So I've given you all the magic matrices. Remember, we developed what these mean in our last lecture here, but you can find it in the class. And the reason why people like these in certain areas of engineering is that they're automatically C2. And that makes sense, and from a very, very high level perspective, right? Because the first curve and the second curve share 3 points. There's just one that I swapped from one to the other. So sort of impose 3 constraints linking them together. Okay, so here's an image of what this looks like. Here's a B-spline. To get a derivative discontinuity is kind of hard to do. Like if I wanted a kink in my curve, what I have to do is like repeat the control point 5 times and make sure that the curve gets stuck there before moving on, and so on. Right, and so here's an example of 2 different curves of the same control points, but interpreted differently, right? So the Bezier curves is going to take every set of 4 and draw an arc, right? And have them be kind of disconnected. The B-splines make one long arc, but it never touches any of the points, except this apparently human computer. Okay. Quick question. If I can draw a cubic arc in the B-spline basis, could I have also drawn it as a Bezier curve? How many of us vote yes? How many of us vote no? How many of us just like can't even, we're just not really there? Yeah. There's still another category I haven't discovered yet. Right. So yeah, the answer is that all of these are just different bases for things built out of cubics. Do you see that? So at the end of the day, any arc that I could have drawn as a Bezier curve, I also could have drawn as a B-spline and vice versa, but the control points would be very different, right? So here's an example where I've taken a Bezier curve, right? See, notice that it goes through the first and the last point here. And I've converted the control points to B-spline control points. They're a little crazy. Similarly here, yeah, we've done the opposite. Yeah. So are there any questions before we move on to the more interesting stuff, the transfer surfaces? Yes?
Which basis do artists prefer? You give them a tool.
The artists prefer that you don't tell them that they're doing anything in a basis. They just want to see the user interface that's intuitive.
Even if they're dragging around points, which one's more intuitive?
Right, so I think typically we use Bezier. So if you play with PowerPoint, what happens is you draw the curve and you kind of draw a bunch of points, right? And then what it gives you is this little line segment which is tangent to your curve at each of those points. And the way that PowerPoint gets around this annoying constraint is that the tangent just kind of like sits next to the curve and it has one control point on one end, and when you pull it out, the other end just goes out too, right? And it just doesn't really explain why that happens. Behind the scenes, those are like the last two control points in one guy and the first two are next. Yeah, they're sneaky. Yeah. Any other question? Yes.
So, sorry, if you cast what shows, those indices came from some relationship between three times the three gamma and like the Duvern's do.
Not quite. So that was specifically for Bezier curves. So here, these points come from the same cubic blossom, but instead of evaluating them at 0, 0, 0, 0, 0, 1, 0, 1, 1, and 1, 1, 1, I've evaluated that function at 0, 1, 2, 1, 2, 3, 2, 3, 4, and so on. And so this has nothing to do with the tangent of the curve. This curve is going to sit like that. It's going to sit inside of these points. It's a little unintuitive. Yeah. So what it gives you is C2 continuity, and what it takes away is control over the shape. Like for instance, it's very hard to draw a B-spline and say, I really want my B-spline to go through this point. That's like a difficult thing, yeah? Because you have to control points that are far away. Okay. One small extension which we're going to defer for now until we talk about projective coordinates, but it's a good vocabulary word to keep in the back of your head, is NURBS. I know you guys have seen this. So if you ever play with 3D modeling software, you've probably seen this weird acronym here. It stands for Non-Uniform Rational B-Spline, NURBS, I believe. Did I get it right? Yeah, and the idea here is that in NURBS, they additionally allow these t values to be not equally spaced. That's not a big deal. It's just like a little more annoying mathematically. And the other thing that they do is rather than using polynomials, they use rational functions. And we're going to see in our lecture on projective geometry that doing that's actually not so difficult in the context of graphs. Okay, but now let's do the fun stuff. Let's talk about teapots. So the real question that I think a lot of you guys took this class for is how to model a 3D surface, right? So all of you guys are excited to go into video game industry. This is where you'll be spending all your time thinking, right? Probably not just drawing curves. And of course, the reason that I've structured today's class the way that I have is that we're going to build surfaces out of curves, by sweeping them along other curves. Okay. This surface is a very famous one. This, I think, was the very first NURBS surface. This is called the Utah Teapot. It was made at the University of Utah, I think, in the 1960s, 1970s. If you look at the actual mesh, it's very retro. It's like made of, orange, yellow triangle things. Right. So when we talk about representing surfaces, there are a lot of different ways that we could do it. Right? We could write it as triangle meshes, which hopefully you're all familiar with from your homework. You can write them as tensor product, which is what we're going to do today. We're also going to talk a little bit about subdivision. And later when we cover physical simulation, we'll talk about some other techniques, like implicit surfaces. These are the zero level set of some function that might evolve over time, and procedural stuff. So procedural rendering will be like, I want to render a whole city, and so I give some rules for how to build a building. Like, my building is this wide and this tall, so it has this many windows. And then I write a piece of software that generates the 3D model for me. So nowadays in the kind of world of machine learning, procedural modeling is making a big comeback, right? Because people are learning, what is the statistical structure of a city, and then how can I use that to generate new virtual world work, for instance. Okay. Right, so what we've talked about so far, and what you did in assignment 0, was to do computation with triangle meshes. These are the world's simplest representation of surface, right? It's just big pile of triangles. But the reason why this is difficult is just like the reason why working with polylines was difficult in our last lecture, right? If I want to take this bunny's ears and pull them apart for some reason, how would I do that? It would be quite tedious, right? I'd have to take every point on every triangle and move them one by one. Yeah, and that's too much work for the artist. Right? So they're simple, they're easy to render, right? That's, in fact, you guys were able to do that in 1 week of this course. But they're not smooth, right? You can see all the facets on the bunny here. And you need a lot of triangles to approximate a nice surface, which implicitly means that there's a lot of points you gotta move around. Okay. So instead, we're gonna think of triangulated surfaces as a tessellation of some nicer representation. So in other words, remember these are the easiest things to draw, but they're not necessarily the easiest things to model in 3D. Okay? And so again, our vocabulary word comes up, which is tessellation. And this is the idea that I have some smooth bunny is really the bunny that I care about. It's not this faceted object I'm drawing on the screen. But in order to algorithmically draw this thing, I cover it on lots of little triangles, and that process is called tessellation. Now tessellating a curve is pretty easy, right? I just sample a bunch of t-values and connect with line segments. Tessellating a 3D surface is extremely difficult. So we'll see one pretty simple strategy for that today. But this continues to be a topic that people study and explore, especially in the world of physical simulation, because there the triangles need to be nicely shaped for your physics to be accurate. Okay, so here's an image of what tessellation looks like. Maybe you make some kind of nerve surface of this dress here, and then when you put it in your tessellation tool, what you get is a nice triangulation of this object. If you're a really lucky person, your triangulation has a property called delta, which means that all of your angles are less than or equal to 90 degrees. That is a property that makes your life very hard to do in practice. Okay. So the question is, how do we model a surface? If it's not just a big pile of triangles, then how are we going to represent it? And the convenient thing we can do is build that upon what we've developed so far in our last 2 lectures. Okay? So in particular, let's say that I draw a cubic Bezier curve with 4 control points. Here, instead of t for time, I'm going to use u for u. Yeah? And so it goes through the first 4 control points. You can see the tangents line up with the first pair and the last pair. So how do you think I'm going to make a surface out of this thing? I'm seeing the right hand gestures, but everybody's too shy to talk. I got to get you guys to wake up in this class. But in particular, if I take P1, P2, P3, and P4, and I make those curves as well, then as a function of u and v, now, what do I get? I get a little kind of squarey patch thing. Yeah? So in particular, now I'm going to draw curves, which are functions of some other variables, and define kind of time-varying control points. And these sweep out everything that I want. Right? So mathematically, I'm going to say that my P1, P2, P3, and P4 are functions of the second parameter v. Does this trick make sense? Cool. Okay. And for lack of anything more intelligent to do, I might as well make P1, P2, P3, P4 themselves cubic Bezier curves. Right? We got one hammer. Let's hit as many nails with it as we can. Yeah? And so what I get is something like this, right? This time-varying set of curves, each of which looks like a cubic Bezier this way. And if I look at the sweep of the control points, that too looks like a cubic Bezier curve. That's turtles all the way down. So mathematically, when we fill in over all u and v, what we get is a nice 2-dimensional surface patch. Patch is kind of the operative word here. This is what people use. If I want to draw a triangle, this is like kind of annoying, right? Like we're really good at drawing square-shaped things. I'll come back to that. And the basic idea here is to take a curve and sweep it along another curve. Okay. And the basic idea is that this thing is called a tensor product Bezier patch. The fun thing about this class, it gives you lots of good vocabulary words to throw around. Okay? And the idea of the phrase tensor product refers that you're kind of taking the product of the horizontal direction and the vertical. Okay? Right. So now let's fill in a little bit of detail mathematically and make sure we understand what's going on. So first of all, if we fix any u or v value and we take the trace in the other direction, what we get is a cubic curve. Fun thing to think about is what would happen if I take like u equals v and like go down a diagonal? Do I still get a cubic curve? Well, you think about that at home. But if we kind of remove all this crazy stuff that we drew, what we really have is a nice surface patch, which is what we were after drawing to begin with. And so this is actually something that's pretty common. If you open up 3D modeling software and you want to model a surface, one way to do it is to specify 16 points. These are the tensor product cubic Bezier patched control points. And what they define is this nice surface here, including all the tangents, its lumpiness in between, and so on. Yes?
Is there any guarantee that, so like what you showed earlier, basically the patches is just a bunch of curves following some other type of curve. Is there any guarantee that those curves don't overlap with each other?
No, yeah, these surfaces can self-overlap. In fact, remember at the beginning of the lecture, we already made a curve that self-intersects. Right? So if we sweep that thing out, we get a surface like this. Absolutely. In fact, when we talk about, so I think your third homework in this course is on cloth simulation. And that's actually a big headache in cloth simulation because if your cloth intersects itself, there's some physical force that happens that needs to make it un-intersect itself. And detecting when that happens is algorithmically really challenging. Yeah. But for 3D modeling, we typically ignore it and we just blame the artist. Okay. Right, so at the end of the day, what does this thing look like? Well, remember, now we're going to start plugging in all of our Bezier basis functions, right? So remember that if I fix P1, P2, P3, and P4, then as a function of U, I can get my curve by putting in the Bernstein polynomials here. I know these are a lot of words that are coming out all at once, and many of them are unfamiliar. If at any time you need me to repeat or parse a little bit, you should let me know, okay? Right, but now, what do we know? We know that P1, P2, P3, and P4 here are themselves cubic Bezier curves, so they also take this form. So what do you think I'm going to do? I'm going to take this guy and plug it in there. Okay? So, what happens when I do that? This is where like PowerPoint is a godsend because I don't have to write it all down on the screen, and it's not that important anyway. Well, if you think about plugging in this expression for P1, right, I'm going to get a bunch of B1, B2, B3, and B4 hiding in that. So when I expand out this giant product of all these crazy terms, I can get a bunch of products of like B1, B2, B2, B3, and so on. How many pairs are there? 4 taking 2 at a time. Right, you end up with 16 points. Yeah, those are your control points. And one way to see that is here, right? So here, all I've done is plugged in the expression for Pi here in terms of its own Bezier curve. And now I've taken the sum to the outside. And what I get is a new set of basis functions for patches. And these are just products of the basis functions for curves. Does this construction make sense? I don't think you guys need to write it down. It's on the slides. And at the end of the day, this is just a very long-winded justification for multiply two things together. Yeah? Okay. So what do we get? Well, a tensor product, cubic Bezier surface, it has 16 control points and 16 two-dimensional basis functions. Do you think that engineers and artists like working with these things? No, that's a lot of points to move around. Yeah? And in particular, if I want two of these patches to meet together in a nice way, there's all kinds of conditions to make that happen, right? Because it's like the product of all the curve conditions along two different directions. You have to handle all at the same time. Okay, so to recap a little bit, a tensor Bezier patch is in a sense quite simple. It's just taking the control points of a curve and dragging them along a second curve, and that thing traces out a surface. And at the end of the day, what you get for basis functions of that are just products of your basis functions for the curves. Okay. Incidentally, if you want to get the tangents and the normals to the surface here, that's something that you guys should have covered in calculus class, right? So to get the tangent, you can differentiate in U to get a tangent this way, differentiate in V to get a tangent that way. And if I want the normal to the surface, I just take the cross product. Remember the cross product is perpendicular to two vectors. And so on your homework, what we're going to ask you guys to do is exactly that. Quick question, is the normal to the curve that traces out one of these parametric lines the same as the normal to the surface? It's a little tricky to think of. The answer is actually no. The normal to the surface has to be perpendicular to two curves, not just one, right? And so this is like a kind of bad piece of overloaded terminology. Right? So on your homework in particular, we're going to ask you to compute surface normals, which are needed to light stuff. And so for your surface to get lit, the way that you're going to have to do that is to take two different tangents and take their cross product, rather than just taking the normal two curves. So I'll let you guys make that mistake on your homework. Because if you don't, your rendering is going to look super weird. Okay. I think I'm going to skip this because I think it's confusing and unnecessary. Essentially, just the same that we developed this crazy linear algebra notation for curves, you can do the same thing for surfaces, but you end up having to deal with like this kind of weird notation involving tensors. I think this is just not fun for anybody, so let's not do it for a long time. Okay. So this construction of making a tensor product works for any of our curve bases, right? All it's saying is draw a curve this way, draw a curve that way, and so on. So you can actually take the tensor product of all of the terms we've introduced in this class so far to introduce a bunch of different types of surfaces, right? So you can have a tensor product B-spline surface, for instance. It would be like a B-spline that goes B-spline this way and that way. Or you take the tensor product of a B-spline and a Bezier curve, I guess. I don't know what you want to, but okay. So the pros here are that these are smooth things and they're defined by a relatively small set of points. But the cons are that they're harder to render, right? You still have to convert this thing to a bunch of triangles. And sampling triangles is a little bit of a pain. You could, for instance, do triangles in the UV plane, but there's no reason why those would be the same size in the 3D shape. And it's really tricky to ensure that your patches meet up in a nice way in this language. In fact, we're not even going to derive that here because it's like no fun at all. Okay. Yes?
Just curious, so this is mostly based on Bezier, and you talked that you also tried to
Mm-hmm.
how do you kind of just drop the Hermite stuff?
No, yeah, you could also have Hermite things too.
Oh.
Yep, there's just only so many slides in it. Absolutely, great question. Okay. And of course, our first example of this type of surface is the Utah Teapot, and here I've shown you the patches. So I believe that this guy is made out of 16 tensor product patches. And the giant headache that Martin had to deal with was that these things meet up in a circle, but they're square-shaped patches, right? So getting those to overlap in just the right way was quite difficult, especially in this like retro 1970s computer graphics hardware, which I'm sure was very expensive and less powerful than what you have on your phone. Okay. One quick extension of this, which is kind of fun to look at, is something called displacement mapping. So the idea is that these are used to derive big, smooth surfaces. And then oftentimes artists want to put like crazy detail, like maybe I'm trying to render a lizard, and so I have big smooth lizard, and then on top of it he has, you know, kind of lumpy skin. And you know, drawing every lump on the skin of the lizard as a Bezier patch would probably be a pretty crazy thing to do. So instead, we use techniques like displacement mapping, where what you'll do is you'll store a texture along the surface that says, at a point UV, I'm going to first evaluate this like a tensor product patch at UV. And then I'm going to look into some image where the pixel at the UV location tells me a displacement along the normal to make. So this is like a way to make the surface kind of bumpy. And this is actually the sort of standard technique. So if you play with tools like ZBrush, this is what's going on behind the scenes. So here's kind of a weird example. So here on the left-hand side, we have the tensor product surface. You can see all the control points sitting here. And the right-hand side, what the artist has done is painted on displacement. So for instance, his bald head here has, I don't know what you call that, texture. But essentially, what it's, rather than modeling that as tons of these little tiny quad patches, I've just stored an image which says bump the surface out a little bit. Right? That's a very easy thing to do procedurally, right? You in your code, you first sample your point along the surface, and then you sample your displacement. Okay, so we're a little low on time, but we'll get started on the next technique that we're going to do. And the next part of our lecture on surfaces is how do we make two patches that meet together and are smooth without creating a lot of headache for the engineer. Okay, and the trick here is to use a technique called subdivision surface. And the basic idea is that subdivision surfaces are going to start with some coarse object, and then we're going to give a rule for taking a coarse object, adding triangles to it, and smoothing it out. And then the actual surface that you care about is sort of the limit of applying that rule over and over and over again until you have little itty-bitty triangles. Historically, by the way, the name Pixar doesn't just come up because I used to work there. It really is historically like where a lot of computer graphics technology was invented. And this was first tested out really seriously in the graphics pipeline in a short called Jerry's Game, which is the first one to have subdivision surfaces and cloth. I thought for fun we'd watch 30 seconds of it. So let me see. Unfortunately, the easiest way to get this stuff now is just on YouTube. The audio is a little quiet. So the very famous 3D models in Subdivision that actually we all use still today when we're writing code to test are these chess pieces. These are publicly available and you can download. And there are a couple things that you guys should look at in Jerry. So for one thing, his face, his nose, and so on, I think are all modeled using this plus displacement mapping. And that's what creates the wrinkles on his face. The other thing to notice is this is the very first, I think, kind of major studio film, or at least short, where they incorporated cloth simulation. So this was in 1997. And if you look at Jerry's clothing, you can see it's moving with him, for one thing. It's also very stiff. You'll see on your homework that makes it much easier to simulate. If you look later, one additional thing, luckily there's no talking, so I can kind of talk over it. I want you to look closely at his arm and the cloth and take a look at what's going on. For instance, in this shot here. Okay, the cloth has a life of its own. Thanks. I think they had to redo a lot of these shots. Also notice that the hair is just glued on his head. So one of the crazy things about this clip is that I believe a lot of the is that I think a lot of the physics was actually just artists created, like they just drew all the curves and shaking it up. They didn't know how to do it. So let's talk a tiny bit about how some of the 3D models in Jerry's game were made, and then we'll pick this up in our next episode. Okay? So the basic idea, which was really groundbreaking at the time, and now is just a standard technique in computer graphics. By the way, that short, I believe, won an Academy Award both for the technology thing as well as artistically, which is kind of cool. And it comes from this observation we hinted at in our last lecture. Remember in the de Castel-Joe algorithm, we started with what you might think of like as a very coarse approximation of your curve, those 4 control points. And then we came up with a rule for making 4 new control points to the left and right side that were a little closer. We could do that recursively and get closer and closer and closer. And that was one example of many where a few simple controls can actually create a smooth object. Right? And so another example here, which is actually roughly the same, is an algorithm called corner cutting. By the way, these are all really fun algorithms because you can just, like, if you're bored in class someday, you can plot a piece of scrap paper and, like, play with them, draw nice smooth things. So the idea of corner cutting is followed. We take every corner in some polygon. For simplicity, I'm going to make it closed instead of having to deal with the boundary. And we're going to take a 1 to 3 split of every edge here. Does the number 3 here matter? No, this is just one of many splits. So I'm going to take that corner and just cut it. Okay? And similarly, I can do that with all the other corners on my object. And what do you see happen relative to the original one? It's a lot smoother. Right? Now what do you think the next step of this algorithm? Do the same thing again, right? And the next step of the algorithm and so on, it's going to make more and more points on this curve. And something you can prove is that this process converges to a smooth object. In fact, in this case, it actually produces a B-spline, which is kind of cool. And so here I've shown you the control points for the curve that we get. And so there's this discovery that there are all these different recursive rules that take a few simple sets of control points and combine them in different ways, where you kind of take the topology of your object. In other words, you take the set of edges and maybe you introduce some extra vertices, and then you place those extra vertices very carefully and iterate that reach smooth surfaces. In this case, this is pretty easy to prove something about. There are other ones, actually, which are really cool, where people have come up with subdivision rules, like just techniques for, like, take a triangle, cut it in half, put the new vertex here, where we know that it approaches a smooth surface, but we actually don't know what the surface is. We just know that it's smooth. This is mathematically kind of strange. But this is the basic idea, is that you cut corners of different objects and smooth them in different ways. And oftentimes, artistically, we like this because the artist can control these points over here, but then what you render for them is the object over here, and these two are approximations of one another without having to deal with all those itty-bitty degrees of freedom. But at the same time, if at some point you decide, no, I really want to edit the finer version of the bunny, what can I do? I can just subdivide that one piece and edit just those subdivided points in a nice adaptive way. Right? So this is really attractive artistically and computationally. So the basic ingredient that you need for a subdivision rule is some base object that you're going to subdivide into a bunch of little pieces, and then a rule for dividing it into more and more pieces. Right? And so here I've given you 2 different potential base objects. One is a bunch of triangles. The other is a bunch of quads. And these are both things that are used a lot in practice. Right? So the left-hand side is called a triangle mesh. The right-hand side is called a quad mesh. A modern topic for research, actually one that my research group studies quite a bit, is how to go from the guy on the left-hand side to the guy on the right-hand side. That conversion is a really challenging problem. In particular, if you look, there are certain vertices like this one here that have 5 neighbors instead of 4. Turns out topologically you have to have those, and it's quite challenging to place those. Right, and so the rules that we'll talk about for these 2 corner cutting schemes are called Loop and Catmull-Clark. Catmull is a particularly famous name. And let's talk just a bit about the loop subdivision. So here, we have 2 triangles. And typically when we talk about subdivision, there are 2 things that we have to do. We have to talk about how to make more triangles out of fewer ones, like topologically, how I connect them together. And then the second thing we have to do is talk about where to put them. Right? So let's talk about the topological piece first. So let's say I have 2 triangles, and I want to make, I'm cheating and looking at my notes here, 8 triangles out of this thing. How could I do it? Any ideas? There are a bunch of different ways, and I'm sure every single one of them exists as some subdivision. Yeah?
Take the midpoints and divide.
Exactly. So I can take every edge and divide it in half and connect those midpoints. And that takes every triangle and divides it into 4. Okay? And that looks like this. So now we have a new set of vertices. They're the new ones, which are marked in blue, and a new set of edges, which are marked in light blue. By the way, a fun thing, one more reference to my class in the spring. Notice that this point here has 6 neighbors. And one thing you can show is that on average that has to happen on a surface. And the more you subdivide, the more valence 6 points you'll find. This is a fact from topology, and in fact, if you look, for example, at that mesh that you guys were working with on your homework last week, and you just count the number of neighbors your vertex has, you'll see that the number of vertices with 6 neighbors is extremely high. And these are called semi-regular meshes because most vertices, but not all, have greater than 6. Okay. So, in any event, we have a way now of taking 2 triangles and making 8 triangles out of them. But what I haven't done is told you where to place the new vertices, right? So if these are points on a 3D surface, a really boring subdivision rule would be to just keep these guys in the plane of the old triangles, right? Then the surface wouldn't really change. So in fact, we want to place those things very carefully. In this course, we're not going to derive the subdivision rules as much as just talk about the algorithm a little bit, because the subdivision rules are a little bit tricky to get right in practice, and we only are allocated 1 lecture on this particular topic, which is too bad. But roughly, the idea is that loop subdivision takes place in 2 steps. The first thing that you do is you place the mid-edge vertices here, and the way that you do that is by taking a weighted average of the 4 vertices that are closest to him, with weights 1, 8, 1, 8, 3, 8, 3, 8. As a sanity check, what's the sum of those 4 numbers? 1? Yeah, which kind of makes sense. You wouldn't want to like extrapolate and go crazy on your surface. Yeah, so this is just some weighted average of this stuff nearby. And one thing that you guys should think about is, like, for instance, 2 triangles and they meet like this, they meet in a flat. What does that imply about the position at this point? Well, it also includes the positions of the guys opposite, right? So it's actually kind of inset a little bit. Yeah? And then the next step of the loop subdivision, after you place the blue points, is to place the red point at the center. And so actually the loop subdivision rule has kind of a weird property that it actually moves all of the points on the surface, not just the new ones that you've introduced. But it does it in a kind of controllable fashion. And to make matters even more complicated, you need a special rule to deal with vertices that are greater than 6. So you have to make sure that the weights add up to the right number. This is not a topic that we're going to cover a lot, but instead I'm going to show you some pictures of what it looks like. And this is the kind of thing, by the way, for your final project, if you're looking for topics you like geometry, implementing these subdivision rules and showing that you can control them in different ways is a good fodder for that sort of thing. But here you see the chess piece from Jerry's game. And you see after we apply the loop subdivision rule several times, what you get back is a nice circularly symmetric object. Okay, so I already see some of you guys packing up your bags, so maybe we'll call it for the day. So in our next lecture, we'll talk about Kaplan-Clark subdivision, which operates on surfaces constructed out of quads. And remember that your nanoquiz is at the beginning of the next class, okay? So get here on time. So I'll see you guys next week and get started with
After you've